Hi guys, my name is Izu and today I'll be teaching y'all about the half-life of a reaction. Um, you probably learned about half-life. Well, first, let me tell you what a half-life is. The half-life of a reaction is the time required for the reactant, I mean, the time required for the concentration of a reactant to fall to one half of the initial value of the concentration. So, like, for example, say that a reactant was like 3 molar and the half life was 20 seconds. In 20 seconds, that reactant concentration would fall from 3 molar to 1.5 molar, since that's half of the um, concentration that happened. Okay, you probably learned about half life like in middle school math, but there probably wasn't like a set formula that you use to derive the concentrations, like the rate constant. But in chemistry, um, the half life of a rate constant, it like differs for the different orders of a reaction. So there's first, zero, and second order reactions, and let's start with first order. Um, the first order reaction, the half life is derived by this. Half life equals 0.693 divided by K, the rate constant. And so, there's still like a lot of stuff that you need to know about first order reactions. Like, for example, the integrated rate law. Integrated rate law for the half life of a first order reaction is AT, which is the final concentration, is equal to negative KT, which is the rate constant. The rate constant times the time plus the natural log of the initial concentration, which is AO. And you can see it right there. The straight line plot for the first order reaction is, it's a straight line, obviously, but the way that the line is, it is an inverse function. So that's why it is relevant. And then it's time, t. So this is how the straight line plot would look for the first order reaction. And the reason why first order like half-life reactions are so common is probably because the half-life is independent of the initial concentration, which is AO. So no matter like even though the concentration changes as time progresses, like the function still stays the same. So that's why the first order reactions are so common. Let's do an example for the first order reaction. Okay. Give me a second to write this out. molecular iodine dissociates at 625 Kelvin with a first order rate constant of 0.271 seconds. What is the half-life? Okay. You can see it. Right when you read this problem, once you see first order rate constant, like an alarm should go off in your head to use the formula for the first order rate constant. So, as we learned like a few seconds ago, the formula for half-life for the first order reaction is half-life is equal to 0.693 divided by K, the rate constant. In this problem, they said that the first order rate constant was 0.271 seconds. So, to solve this, you would do 0.693 divided by 0.271 seconds to find the half-life. And let me use my calculator real quick. 0.693 divided by 0.271. And the half-life of this reaction should be 2.557 in seconds. So what that means is every single time 2.55 seconds passes, the concentration of this certain reaction will be cut in half, which is the basis of the half-life reactions. Okay. Now we can go to a second order reaction and explain that. The second order, these reactions are, the half-life is expressed as half-life equals 1 over the rate constant times the initial concentration of the reactant. So it's derived as such. Next, we should probably learn the integrated rate law for the second order reaction. And that is 1 over the final concentration, which is AT, is equal to K times T, which is the rate constant times time, plus 1 over the initial concentration of the reactant. So that's what the integrated rate law looks like.